we have come to the last big theme in the course of soft matter, namely membranes. Membranes, in some sense, are the quintessential soft matter. They, like polymers, they are objects in space that have an entropy and an energy that combines into a free energy that describes their ultimate shape and properties. They consist of multiple components that can mix or demix, like the solutions, and like the viscoelastic materials, they combine solid and fluid properties. They're a little bit different than the viscoelastic solutions of polymers in the sense that now whether the membrane behaves like a solid or a fluid will depend on the direction. If you think of a sheet of paper, it's like an elastic surface in 3D, and it has a bending energy. If you bend it, you need to exert some force, do some work to bend this sheet of paper. And for membranes, we have the same. However, unlike for paper, for a membrane, if we move within the plane of the membrane, the lipids, the particles that make up the membrane, and also other particles that live in it, are free to move around. In plane, a membrane is a fluid. Out of plane, it behaves like a solid. Before we go to discuss the mathematics of all this and build physical models, it is good to quickly recap why we are interested in membranes, where we find them, and also what they are made of. Membranes are pretty much everywhere in biology. Every cell has a boundary that consists of a plasma membrane. Eukaryotic cells have a lot of internal structures that are also bounded by membranes quite often. And many industrial applications use artificial membranes, either made from the same kinds of molecules as biological systems or from different kinds of polymers that have similar properties. If you want to build a membrane in a watery environment where most cells live, the thing to do is to pick a molecule that partially wants to be in water and partially does not. And the quintessential molecule for that is called the lipid. It's essentially a fat molecule. And lipids consist of two pieces, a head and usually two tails, though there are examples with three, and cholesterol is like a tiny lipid with one. The head region is usually polar. It can be charged or not, but even if it's not charged, it can have a dipole moment. And polar molecules, as you might know, are easily dissolvable in water thanks to the dipole moment of water itself. So we will have a polar head region, which typically consists of sub-pieces that we will leave aside for now. And then in addition to the head, it has the two tails. And the tails are typically very long and sometimes straight and sometimes kinked. And the tails are essentially long chains of carbohydrates. A carbohydrate chain, as you hopefully know, is essentially oil. And you all know that oil does not dissolve well in water. So if we throw a lipid like this in a watery solution, well, if it's on its own, it will just be unhappy. But if there are many of them, what will happen is that they will spontaneously make a bilayer, a double layer of lipids, where all the heads are on the outside so that they are facing the water, and all the tails are on the inside so that they are not interacting with the water at all. Right, so what we are going to get is a lot of heads together on one side, a lot of heads together on the other side, tails sticking inwards, such that water molecules will typically not interact with the tails, but only with the head. This is a 2D drawing. This will extend in 3D. If we have just a sheet, it will still have free sides, so this thing will spontaneously close up on itself and make a vesicle-like structure with a double layer of lipids around it. You might wonder if the lipids cannot all just make a structure like this, where they all sit in a circle and stick all their tails together. And the answer is, well, they can, if they have heads which are much larger than the tails. And so this structure is known as a micelle. It's something that soap molecules tend to do with the little pieces of oil that are floating in the water, and then they can be washed out. But the lipids that make up the membranes that we are going to be interested in are more or less cylindrical in shape, and therefore will stack nicely together. Of course, In practice, they're not all exactly cylindrical. Some have heads that are significantly larger than the tails and will be a more cone-like shape. Others have heads that are smaller than the tails and will have a wedge-like shape, and together they determine the properties of the bilayer. In the plasma membrane, that's the boundary of every cell in your body, there are a lot of different types of lipids included, and also the two leaflets, the two layers of the bilayer, are typically of different composition, and therefore they can control in very fine detail the properties of your cells. In artificial systems, we can easily make these lipids, we can synthesize them, and then we can put them together, and they will spontaneously make membranes. We can make artificial membranes that consist of just one type of lipid. We can also make membranes with 2 or 3 types, and then, as I said, you can mix or demix depending on the properties of those lipids. And one of the characteristic properties there, which is something I already sketched here, is that the tails can all be straight like this or have a kink like that. And a kink in a tail typically happens if you have an unsaturated bond. So if you look at the ingredients in your food, typically you will have a distinction between saturated fats and unsaturated fats, and the unsaturated ones are the ones that have kinks in their tails, are supposed to be less healthy than the saturated ones. For our purposes, this kink in the tail will actually have a big effect. Because if a lipid has this kink, then it has a fixed thing that can rotate and then disorient. And so the orientation of the tails will be random. Whereas if there are no kinks, we have fully saturated lipids, the tails will be relatively straight, and we will have a large collection of straight tails all next to each other. And this will give us 2 different phases, known as liquid ordered, where all the tails are ordered, and liquid disordered, where we have a more or less random configuration of tail orientations thanks to the presence of the kinks. In real cells, but membranes don't just consist of lipids, they typically have a lot of proteins in them, and those proteins functionalize the membrane. They act as transporters, as receptors, as adhesion molecules, and many other things. And because they are in the membrane, they will of course influence what's happening with the shape of the membrane, and also sometimes with the composition of the membrane, and we will discuss that too. For today and the next lecture, we will focus first on the lipid bilayer membrane itself, and then later we will include the effects of proteins there. Some numbers. These lipid molecules, they're not super big. They're typically 2 to 3 nanometers in height, which makes the bilayer having a typical thickness of 4 to 5 nanometers, which is not very much, especially if you think that the typical cell, a eukaryotic cell, will have a radius between 10 and 100 micrometers. And so the lateral size of the membrane is way larger than the thickness. And therefore, in practice, most of the time we are going to approximate the membrane as if it is an infinitely thin sheet, a 2D surface living in 3D. People have looked at the difference of the leaflets, and sometimes a difference in area between the leaflets or friction between the leaflets can be important. But for the simplest models and for simple experimental systems that consist of just one type of lipid, these things do not matter so much, and we can get all our experimental results very nicely from a theory where we indeed treat the lipid bilayer as if it is infinitely thin. So how are we going to do that? Well, think back of the way we described polymers in space. What we did is that we said, well, we have a curve in space, and what we want is a local coordinate system on the polymer to describe its properties, because any choice of external coordinates will be arbitrary. However, we did start with an external coordinate system where we said, well, we define here a coordinate system with some arbitrary origin. And then what we can do is we can say, well, every point on the polymer we can write as some vector from that origin as a function of a proper parameter. And for the polymer, we chose the arc length, right, the length of the distance that you have traveled along the polymer. And then what we did is we said, well, we can now construct a local coordinate system on the polymer by looking at the tangent. which was a unit vector, its derivative, which gave a magnitude and a direction, we had proven that because the tangent is a unit vector, its derivative will always perpendicular to the tangent, and so that was the normal vector, the magnitude, and then the derivative, the magnitude of the derivative was the curvature, and then by taking simply the cross product of the normal and the tangent, we arrived at the third direction, the binormal, which in this case would be pointing into or out of putting out of the paper. For our membranes, we are going to do pretty much the same thing, but there are some differences. Right? For our polymer, we had one curvature, and then we also had a torsion describing the shape of the polymer. For the membrane, because we have a 2D surface, we will have two curvatures because there are two tangent directions. We will have no torsion unless we can make a membrane that has a torsional property, but we can still describe it all in terms of the two curvatures. And unlike the polymer, we will have no arc length. And the reason for that is that there is no unique way to define an arc length for a two-dimensional system. Right? So, but many of the things that we will see will have close analogies to this three-dimensional description of a curve. So I'm very bad at drawing 2D surfaces, but think of a 2D surface like this, and you can immediately see I can indeed describe this as a collection of points in space. Again, every point has a vector with respect to some reference origin, but now I'm going to need two coordinates. I'm going to need, say, a coordinate along this direction and a coordinate along that direction. Or if you think of another familiar surface in space, think of the surface of the Earth. It's a 2D surface in three-dimensional space. If you want to uniquely specify a point on the Earth, we need both a latitude and a longitude, or as we would do as physicists, right, we use spherical coordinates and we need both the phi and the theta angle to uniquely specify where we are. So we can do that here too. And so what we say is we define some coordinate system, and it can be anything, simply by drawing some lines on the surface, and then walking along one line gives us one coordinate, walking along the other line gives us the other coordinate, akin to walking along the line of the polymer that we did with the arc length. And then for every point we can write the point on the surface as a function of these two coordinates. And I'm going to write these two coordinates, well, I can either write them as u and v, but it's sometimes handier to sum over things, so I can also write them as u1 and v1, u2. So these are my two coordinates on the surface, and I have now a point on the surface. And if I want to describe locally what's going on, what I'm going to need is a coordinate system locally. And this is going to be very similar to the local coordinate system that we had for the curve. We took the tangent vector as the direction, right, the tangent to the surface, which is the direction of the change of the position vector r. And we can do the same thing here, changing one of the two variables, right? So either u or v, or u1 or u2. This is going to give us two basis vectors. So I can define a local tangent basis to our surface in 3D. Right? So for example, if my surface is curved like this, I effectively say, well, I have a tangent plane now to this thing. The tangent plane is flat, right, through a tangent line, and also in the other direction. And this defines then a local coordinate system at that point of the surface. And so my two basis vectors, and I'm not going to normalize them this time, the two basis vectors that I have are going to be E1 and E2, or E1 or EU and EV, the derivative of R to U, and EV, the derivative of R to V. Right? Or if I use the 1, 2 notation, EI, where I can now be 1 or 2, not 1, 2, or 3, is the derivative of R to UI. The reason why I don't normalize this is because this will introduce extra factors. In the case of the polymer, the normalization was for free because we wrote things in terms of the arc length. And then the derivative to the arc length always gives a normalized vector, and that was nice and easy. Here we're not going to do that simply because it's not necessary. We will absorb this constant differently. Right, so we have now two basis vectors of the tangent plane. Of course, for a full 3D system, we are going to need a third one. And since we already have a plane and we already span this plane, we can simply find the third one by taking the cross product of the other two. And that will give us a vector that's normal to the surface, and indeed this will be our normal vector. And the normal vector is then defined as the cross product of the other two. And the normal vector will be normalized. This is again a convention that people use. One of the reasons is the normal vector itself better be normalized. It will make its interpretation easier. So we're going to define our normal as the cross product of EU and EV divided by the length of this thing. Or again in numbers, E1, 2 divided by this length. Now, if I want to calculate this length, this magnitude, this has to do with the magnitude of the vectors itself. And the thing for that is the inner product between the vectors. And the inner product will give us a sense of the length of the vectors. And now the inner product, since these are vectors that are still defined in ordinary 3D space, the inner product is simply the dot product, which we know how to calculate. But the inner product of these two vectors will no longer necessarily be just, it will be the length of the vectors if we take the inner product of themselves, but the inner product between E1 and E2 will not necessarily be 0. Only if we have chosen a coordinate system that happens to be locally perpendicular, which is known as an orthogonal coordinate system, then that will be the case, but in general it will not. And we can always make a coordinate system orthogonal, but again this will introduce correction terms, and the easier way to work is by including this into a tensor, which is known as the metric tensor. Right? So the metric tensor, as the name suggests, it measures lengths in areas. And so it's defined, its components are defined, right? The ij component of the metric tensor is defined as the dot product between ei and ej. This one is symmetric, so if I flip I and j, I will get the same number. So in general, I will have three numbers here, right? The dot product of EU with itself, the dot product of EV with itself, and the dot product of EU with EV. And as I said, this last one is now not necessarily 0. This metric is the thing that shows up in, if we want to calculate now the area of the total surface. Right? So the total surface area is an integral over the whole membrane that can be calculated now in terms of these local coordinates, U1 and U2, with the square root of the Jacobian of this system, and that Jacobian turns out to be the same as the determinant of this metric. The proof of that takes some lines, and you're welcome to look it up in the notes. Right? But what's important to know is that the area of the membrane is the integral of the Jacobian, which is the determinant of this metric, U1 integrated over U1 and U2. And this, of course, is why this tensor is known as the metric tensor. Now, this area already gives us one way of defining an energy. If you talk about soap bubbles, soap films, they are essentially liquid surfaces. They have no resistance to curvature, and the energy of a soap bubble is essentially some constant, which we are going to call the surface tension, energy per unit area, times the total area, which we can then calculate in this way. And what you find if you do that is if you make a single soap bubble Obviously, the soap bubble is going to be a sphere, which will not surprise you. And if you have two soap bubbles that are sticking together, it will depend on the pressures inside, but if the pressures are equal, we'll have a flat surface between them. If the pressures are not equal, we will have a curved surface, which you can also calculate using this area energy. Now, for our membranes, it's not going to be that easy. And that's because if we try to curve or to bend our membranes, this is going to require some work. In other words, there's energy stored in bending a membrane, just like there was energy necessary to bend a polymer, which gave us the worm-like chain correction to the freely jointed chain model. So if we want to calculate what this curvature energy is, we need to calculate the curvature of the membrane. Now, there are various ways to do that, which all give the same result, but let me illustrate by two. Let's start with the one that is inspired by the curvature of the polymer. And the curvature of the polymer was the rate of change of the tangent vector. Right? We took the derivative of the tangent, that was a magnitude and a direction. The direction was the normal, but then the magnitude defined the curvature. Here for the membrane, of course, we have two tangent vectors. So the rate of change of the tangent vector is going to be a bit of a ill-defined thing, because which direction should we pick? However, we only have one normal vector. And the normal vector is something that we can quite easily use to define a curvature. Think of again, the sheet of paper as an example. If the paper is flat, then the normal vector is all parallel to each other, and the curvature is 0. If I now bend the sheet of paper, the normal vector will start making a turn, and the more that I bend it, the sharper the turn of the normal vector will become. And therefore, the rate of change of the normal vector, which we will write as the divergence of the normal vector, is a good way of calculating the curvature. And in fact, the curvature that we will end up with is indeed proportional to the gradient of the normal vector. So I'm going to call this the mean curvature. You will see why in a second. And in terms of the normal vector, it is defined with a minus sign, minus a half times the divergence of the normal. The minus is just to make the curvature of a sphere come out as a positive number. And the half, again, is also to make the curvature be consistent with another definition. But it's the rate of change of the normal vector that is important here. The other thing that we could do is say, well, we can look at how things change indeed with the tangent vectors. Now, of course, we are going to have two directions. So how should we think about that? Well, if we think of a curve in space, I can also calculate the curvature I can calculate it from the tangent circle, or I can locally approximate this curvature around the minimum, or this curve around the minimum, with a parabola. Right? If I have some curve in space, I can locally always draw a parabola around such a tangent point, and then what we have proven, or what you guys have proven in the problems, is that the value of the second derivative, right, the coefficient in front of x squared in the parabola, that one is related to the curvature itself. So in 2D, we can also describe locally our surface with this parabolic shape, but then what we have to do is to include the full 2D property. Right? So if I write the shape of a 2D parabola, right, I have a position z as a function of x and y. Right? So I have an xy plane and a z direction. And my parabola is now an object, right, a 2D a paraboloid, if you will. Right? That's, if you rotate it around the z-axis, it's still a parabola. And so what we can do is, if this parabola has its 0 at 0, what I have is that locally the z-coordinate will be given by a half times x, where x is now in the xy plane, dot some matrix, or actually a tensor, plus, of course, higher order terms. Right? So this is similar to the parabola in 1D, but now we have a 2D. And then what are the coefficients of this tensor C? Well, these are simply the second derivatives of this function Z. So Cij is the second derivative of this function Z of x1 and x2, or x and y, to second derivative to x, second derivative to y, and the mixed second derivatives. Or if I now want to express this not in terms of z and x and y, but in terms of this vector r that we had before, this is pretty easy. The vector r is mapping from some reference coordinate system to this thing, and the component of the z direction is simply the component of r along the normal vector, the perpendicular vector here. So this is the second derivative of r with respect to, now it's xi, xj, now with dot product with the normal vector that we have here. And so the components of this curvature tensor are also going to give us the curvature. Now these are three independent numbers, but it's symmetric, so it's only three numbers, not four. And components of tensors are going to be dependent on the coordinate system. But as we know, there are properties of the tensors that are independent. And those properties are the eigenvalues or a certain combination of the eigenvalues, such as the trace and the determinant. And the eigenvalues are going to be two eigenvalues. It's a two-dimensional surface after all. Those we call the principal curvatures. The directions that correspond to those, the eigenvectors of those eigenvalues are known as the principal directions. And if we would have chosen u and v to lie along the principal directions, then the curvature matrix and also the metric tensor would be a diagonal one. And what we get is just two curvatures for the two directions. Now, the quantities that we want to work with, this h, is going to be the mean curvature. That's simply the average of these two eigenvalues, or it's half the trace of this curvature tensor. The other one that we can then make is the product of the two eigenvalues, or the determinant of this curvature tensor. So we're going to have two coordinate independent curvatures, one which is linear in the eigenvalues. So if I call the eigenvalues kappa 1 and kappa 2, then my mean curvature is the same h, is going to be a half kappa 1 plus kappa 2. And I can define a other number which is known as the Gaussian curvature, and you can guess why, which is given by the determinant of this tensor. The mean curvature, as you can see, is linear in the eigenvalues, and the Gaussian curvature is quadratic. As you can prove, and again, this is something that you're welcome to look up, but I'm going to skip over, the mean curvature will depend on the choice of embedding, but the Gaussian curvature does not. And this is related to the fact that if you live on the Earth, you don't actually have to leave the Earth to see that the Earth is a sphere. Another way that you could do it is to draw a very big triangle and then measure the angles of the triangle and sum them up, and you will find that the sum of the three angles is larger than 180 degrees. And that's because the Earth has a positive curvature. And from that positive curvature, from that number and from the length of the size of your triangle and so on, you can even determine what the radius of the Earth is. That this property is intrinsic to the surface and therefore not dependent on the fact that the surface lives in a larger dimensional space, Gauss thought to be a very remarkable thing. And when he had proven it, he then also called it his remarkable theorem. And so this is where the Gaussian curvature comes in. However, the Gaussian curvature is not going to be very important for us, and that has to do with something else that has to do with integrating over a whole surface. What we will see later, and this is another theorem known as Gauss-Bonnet, is that the integral over the Gaussian curvature over a whole surface will be just a constant number. And constant numbers in energies typically don't matter. However, if you punch holes in the surface, it will matter again, so we are going to encounter it. The mean curvature, however, will be the main workhorse for the description of membranes. So as I said, these are related to the trace and the determinant. We have to be a little bit careful though. This Cij, even though it looks like a matrix, it actually is not. It is a tensor representation of this second, what is known as the second fundamental form. And so is the metric tensor. It also means its components can be put in a matrix form, but it really isn't a matrix. A matrix would have, in this notation, one index up and one index down. These two do not. And so if we want to take the trace of this tensor, we need a correction factor for that. And the correction factor is going to be related to the metric. It's actually the inverse of the metric. Right, so we are going to define an inverse of the metric, which I'm going to write with upper indices, which is the matrix inverse of if I would write this one with lower indices, or properly defined, because this is a little bit sloppy since they are not actually matrices. I can write that if I calculate this number, where I now sum again over the index j, then I should get a proper matrix, which actually is the identity matrix. Or in tensor terms, right, I get the identity tensor if I take the metric tensor times its inverse, which obviously is what should happen. And now the trace of this representation of the tensor, this Cij, I can get by taking by summing over not the diagonal elements, but first multiplying it with this inverse of the metric. And this is like we had in the upper convective Maxwell model. It's correcting for the fact that we are now in a different coordinate system. Right? We are using coordinates on the surface, the EI and the N, and those have a correction factor because they are not Cartesians. So for the mean curvature, h, I can write this as a half times the trace of the tensor C, the curvature tensor, which I can actually calculate as a half times Gij Cij. And likewise for the Gaussian curvature, it is the determinant. And this one I can calculate by taking the determinant of writing Cij as a matrix, but then I have to divide by Gij, or I can also say it's the again the inverse of the determinant of the inverse multiplied with the thing. All right. So this gives us the two curvatures, and like what we did for the polymer, we can now say, well, the energy is going to be a function of the curvature.